that. Just come to my office or send me an email. All right, so we've had a bunch of questions in office hours about the structure of certain proofs, and I want to spend some time going back and talking a little bit about these sort of range type arguments and null space type arguments, because the sort of arguments that we're doing here are not going to disappear. And I want to make sure that we nail down what the technique to proofs is. And I suspect, based on my grading of the exam so far, that we're going to have to be a little bit more concrete about like how we approach proofs of these questions, and that we're like sort of work together through like the structure of these arguments, right? Because they're very common. And the idea here is that I want you guys to pick up enough expertise in these types of arguments that you can carry them forward into the classes you got to take. Because even those of you that have the minimalist proof stuff left are still going to have to take a quarter of modern algebra and a quarter of real analysis, which are basically all proof, right? And pretty gnarly, as it turns out. So I really want to nail down the sort of common structures here. So let's walk through the argument here that the range. So we're going to do two arguments here. We're going to I think I sort of quickly went through the argument that the range is a subspace, but I also want to talk about the argument. What was the other one people wanted to see? The relationship between injectivity and the null space. So last time we made the assertion, let's talk about this one first, and then we'll talk about the definitions and how they show up. So there's this theorem that says that if T is a linear map between vector spaces, then the following equivalence holds. So if you are a linear map, then injectivity is equivalent to having a null space consisting of the zero vector. For those of you that saw this in my office hours, I apologize for doing it again, but it's good for you. So that means finish. Then T is injective if and only if the null space of T is equal to zero. And the reason I want to pause for a minute and take some time to look at this argument is that the ideas of this argument are common and they will recur. And they require that you know the definitions as well. So before we get started, we should make sure that we remember what all of these things mean. What is it that characterizes a function being in this space? So what does it mean for T to be an LVW? What do I mean? What can I say about T? Okay, so yeah, so I heard this. I heard T is linear, which is great. And then I also heard T preserves, well, we can say T is additive and homogeneous, which is the same thing as saying T of x plus y is equal to Tx plus Ty, and T of Cx is equal to C of Tx. Okay, so that's got to be in your head when you're looking for these things. If I say something is linear, it's almost certainly going to be the case that if I'm making a proof about a function that's linear, one of these properties is going to show up. Okay? And then the additional property, which was a theorem, which is T of 0 is equal to 0. Linear maps take the zero vector to the zero vector.
Just on like exam and all that, when we're stating linearity and like homogeneity and all that, do you want us to also say like for all x and y?
So if you are making a definition, if you are formally defining something on an exam, you absolutely should have the quantifiers in there. So like if I was not just like quickly writing down the properties and I was being asked to do this formally on the definition, you better believe I'd write for all x and y and v. And here I would say for all c and f and for all x and v. So on an exam, yeah, the quantifiers matter, right? I mean, they don't matter so much that you're going to like, you know, going to take an axe to your exam if you leave them off, but you know, they matter. They're part of the definition. Okay. Okay. So what does it mean for T to be injective? So this is linear. What do we mean by injective?
T at or V of T with T of V. is equal to T of W, then V has to equal W.
Okay, perfect. The algebraic definition of injectivity is if T of V is equal to D of W, then V is equal to W. That's what it means for a function to be injective. If this, then this. What does it mean for the null space of T to be equal to the zero vector? What is the null space of T? Like if I just told you, hey, what's the null space of T? Okay, so it's a set of vectors in V that have the property that T turns them into the zero vector. Okay, so if I say the null space of T is equal to 0, what do I mean? What does this actually mean to say that the null space of T is equal to 0? Okay, so what that means is if this is true, it means anytime you see an expression that looks like this, if it was true that the null space was equal to 0, and I wrote this expression down, what can you conclude? U has to be the zero vector. There's nothing else that could do it, right? If the only vector that T sends to 0 is the zero vector, you don't have a lot of choices for what U could be. U must be 0. Okay, now how does an argument that involves injectivity typically work? Or null space typically work? So what we're going to do is we're going to do this in the forward direction, the backwards direction. Okay? Because the structure of these arguments is common. The interplay between belonging to a certain set or the size of a set or function properties, these have the same kind of structure. Assume T is injective. And you are not Sheldon Axler. If you want on the side of your proof to write what it means for T to be injective, you should write it. You don't have to. Your proof doesn't have to include that, but it might be nice to know, oh, well, if T is injective, then I know that TU is equal to TV is going to imply that U equals VU. I just leave that as a note to myself. If you do an argument and you don't use the hypothesis somewhere, something went wrong. Okay, now, what are we trying to show? Oh, we want the null space of T to be equal to 0. That's what we want to show. I'll make a note to myself. I want to show that the null space of T is equal to 0. But that's kind of a crappy thing to have to show. I'd really like to show some sort of equation. So an equivalent thing to showing that the null space of T is equal to 0 is to show TU equals 0 implies that U is equal to 0. This is equivalent. These are the same statement, right? To say that this statement is true, to say the null space of T consists of only the 0 vector is the same as showing that T of U is equal to 0 forces U to be 0. And the reason we're going to use this in these null space type of arguments is because it gives us a starting place. I'm going to start the argument by writing TU is equal to 0 down. I'm going to try to force it to mean that U must have been the 0 vector. So null space is equal to 0 is great, but if you don't have the sort of expression to go with it, you have nowhere to start when you're doing one of these arguments. Okay, so this is what I want to show. I'll box it up. I want to show around it as a hook to myself. So I remember, okay, these are the same. This is something I can start with. So that's what I'm going to start with. Suppose that U is in the null space of T, which is the same as saying TU is equal to 0. And I remind myself over here, way on the side, I really want this eventually to force U to be equal to the 0 vector. That's the goal. I'm starting with that, and that's my goal. Get here. Because that would mean that the only vector in the null space was the 0 vector. So suppose U is an arbitrary element in the null space. That means this equation holds. Now, Axler, because he already knows the answer, is going to give you the most efficient possible proof, which is, oh, well, you know, another vector that's equal to 0, when you apply T to it, is 0. T of 0 is also 0. Why would I do that? What is the point of even writing this expression down? Yep. Because I want to use this, right? I need an expression that relates T's together. This is what I'm trying to apply, but I can't apply it unless I've got T of something is equal to T of something. So I gotta get another T from somewhere. Well, that's a convenient place to get one. Well, if this is equal to 0 and this is equal to 0, then that means that T of u must be equal to T of 0. And now I'm ready. I'm ready to, I've got this hammer. I've been waiting. It's just sitting on the table next to me and I'm looking for a nail to hit. Well, there it is. There's my nail. I can hit it because that is this. It's the right form. Oh, I was doing an injectivity argument. So to do an injectivity argument, I need to force an expression like this to show up so that I can conclude what injectivity means. So now, by injectivity, now that I've set the nail up, u is equal to 0. Oh, that's it. You're done. What have you shown? If u is in the null space, then u is equal to the 0 vector. That's precisely what it means to say that the null space of T is just 0. So when you're doing an injectivity argument, your goal should be build a nail that you can hit with a hammer. Right? We're going to do this in the other direction. Are there any questions about this direction? I know this is not a complicated argument, but it exhibits things that I want you to notice about these proofs. An injectivity argument is always going to involve evoking this definition at some point. Okay? Questions before I erase this and flip it around the other way? All right. Now, your hammer is different. You have a different tool. I don't know, it's not a hammer, it's a screwdriver or something. In this version of the argument, we have a different tool because this time we're going to assume that that the null space of T is equal to 0, which means secretly, we know that our hammer there is, if I see something that looks like T of u is equal to 0, then I'm going to say u is equal to 0. That's the hammer I've got this time, right? If I get this expression, I can reduce it to that one. So it means for the null space to be nothing but the 0 vector. And this time what I want to show, this is a little bit trickier, but we want to show that if TU happens to be equal to TV, then it must be the case that U is equal to V. I need to show that this logical statement holds. And again, the reason I write this down, not that T is injective, but the algebraic condition is because it gives me a starting spot. I'm going to start by writing down TU is equal to TV and try to wiggle things around until I can hit it with this hammer. Right? So assume TU happens to be equal to TV for some U and V in V. How on earth am I going to manipulate this thing so I can hit it with this hammer? Yep. All right. TU minus TV is equal to 0. And now, just like in the last argument, the linearity of T is going to come into play, right? Because I still don't have a single T applied to a single vector. I've got these two T's. How am I going to get rid of them? It's linear. Oh, there it is, the nail waiting to be hit with the hammer, right? Because now I've got an expression that says T of a vector is equal to 0. If I see T of a vector is equal to 0, I get to say the vector is the 0 vector. I mean, that's what this meant. That's the condition. This is the hammer that came with it. Oh, T of a vector is equal to 0. That means U minus V is equal to 0. That's just this statement right here. The hammer that we've been waiting to wield. That means that U is equal to V. What have we shown? If TU is equal to TV, then U is equal to V. That's the definition of injectivity. So TU equals TV implies that U equals V. So T is injective. Again, very common structure. The condition gets you something that you can hit an equation with, and then the whole rest of the exercise is manipulating things so that you can apply this idea. Okay? And the reason that we're sort of spending a little bit more time at the beginning talking about this is because this stuff starts to get kind of tricky. right? When we start talking about these abstract maps on abstract vector spaces. Okay. So we talked about, that was the proof I assigned you guys to read, I believe, right? Like last time was that one. So the next thing I want to talk about is what Axel says, the result so important it gets a dramatic name. The fundamental theorem of linear maps, which is really the rank nullity theorem if you took 206. So he says the following. Fundamental theorem of linear maps. He doesn't actually refer to it by the name rank nullity theorem because basically nobody says nullity anymore. But you know, if you took it out of Lay's book, I think he still calls it that. So yeah, secretly this is the rank nullity. If so, suppose V is finite dimensional. I think everybody got this question right on the test, by the way. Everybody got what finite dimensional meant. Congratulations. I was happy. T, L, we'll talk about, I'm going to have the exam done, I think, by Thursday. So we'll talk about, like, on Thursday what the plan is going to be. Then, range of T is finite dimensional. And I'm going to put the and up here. And the dimension of V is equal to the dimension of the null space of T plus the dimension of the range of T. That's weird. Why is that statement weird? That should strike you as odd. And maybe you use this in linear algebra and never paid any attention to it. What is weird about this statement? Where does the null space of T live? What vector space does it live in? V, right? The null space of V is a set of vectors in the domain. Where does the range of T live? In W. So somehow the dimension of V is built up out of an object, the dimension of a subspace in its domain, and the dimension of a subspace in its range. That's an odd, it should strike you as odd, right? That T, somehow T is dividing up the behavior of the vector space V into a piece in its domain and a piece in its range. It's an odd theorem. You probably never thought about it before, but it's weird. Now, of course, the reason you never thought about it before is because when you learned it in the past, you learned it for n by n matrices. It's way less weird in the land of matrices. Okay. All right, now, before we go on to prove this thing, I want somebody to interpret for me what this means. Like, what does that actually mean? We got this statement here. It's like all these dimensions written all over the place. Axler says it's fundamental. What does it mean? Or basis. Okay, so basis of V is the same length as so yeah, exactly, right? Like the number of basis vectors that like describe the things that go to 0 and the things that don't go to 0. That's what the range is, right? Is everything else. It's one way of thinking about it, right? So it's like, these are the things that get sent to 0. And this is the size or the basis for everything that didn't get sent to 0. Right? I mean, that makes it less weird, right? That we're saying somehow the dimension of the original vector space, the size of the original vector space, the size of a basis of the original vector space can be thought of as a chunk that got sent to 0 and a chunk that didn't get sent to 0. And that's how the proof is going to work for this. We're going to look at a basis for V, or for a basis for the null space, and we're going to say, okay, well, take the null space, extend it to a basis for all of V, and then we just have to show that the stuff that didn't get sent to 0 helps us get a basis for outputs. So linear maps are basically described by the behavior on things that get sent to 0 and the things that don't. You might secretly in the background think that there might be some sort of direct sum of vector spaces running around, but don't get tricked, because remember, this is in V and this is in W. Okay. Okay. This theorem turns out, by the way, you might think, my first response when I learned the rank nullity, the fundamental theorem of linear maps was to say, okay, well, so what? Right, that's trivial, who cares? But it turns out that a lot of the stuff that has taken us pages of proof in the earlier homework exercises are basically immediate once you have this, which is ridiculous. How do you prove it? So what we're going to do is we're going to chop V up into the vectors that are in the null space of this map T, and then everything else. So let's let U1 to UM be a basis for the null space of T. By the way, why does null space of T even have a basis? Why am I allowed to say that? You don't have to write this in the proof. I'm just curious. Does anybody know why? Yep. Because it's subspace. Every subspace, every vector space has a basis, right? Finite dimensional vector spaces have a basis. Why is the null space of T finite dimensional? Because V is finite dimensional, and the finite dimensional subspaces of a finite, or sorry, subspaces of finite dimensional space are finite dimensional. These are all things we've had to prove in order to do this, right? So even though I'm not mentioning it, there's a lot of theory that we've already built that's active. Okay? So U1 through UM is a basis for the null space of T. So the dimension of the null space of T is M. Whatever it happens to be, it's M, right? I know as a finite list, however long it is, that's the dimension of the null space of T. So now what should we do? Well, is this linearly independent if I think about it as a list in V? I mean, if it was, well, yeah, right? These are vectors in V. It's a basis of vectors in V, which means it must be linearly independent in V. So since U1 to UM is linearly independent, we can extend it to a basis for the whole space. It can be extended. To a basis for V. And we might as well write down, if we're extending to a basis for V, let's call those vectors V1 through Vn. So U1 up to UM, that was the basis for the null space. And then there's some extra vectors, V1 up to Vn. This thing all together is the basis for V by the extension limit. Okay, so what's the dimension of V? M plus N. Now, if I could show that these dudes right here, that's the missing piece, right? I want the length of this list to be the same as the dimension of the range of T. So I need the range of T to have a basis of the same length. Any ideas about where we might get a basis for the range of T that is of length N? I mean, I've got these useful V's sitting around. Could I do something with them? These are in the domain, yeah. But I don't need a basis in the domain. I need a basis in the range of T. Yep.
Phi T.
Ah, well, that'd be great. If we could show that TV1 up to TVN was a basis for the range of T, that'd be great. Then we'd have the list of the right length, right? If I could show that this was a basis for the range of T, then the dimension of V would be equal to the dimension of the null space of T plus the dimension of the range of T. Because this is of length N. And so it would be M plus N, right? But how are we going to do that? What tool do we have to work with? So yeah, it better be the case that we're going to have linearity running around in the background, right? How do I define the range of T? Okay, good. Okay, so range of T is equal to TV, where V is in V, right? Do I have a way that I can express all vectors in V? A useful basis for V? I erased it. For any V in our vector space V, V is equal to C1 U1 up to CM UM plus D1 V1 up to DN VN. Why is that true? Because I made this a basis, right? Remember, this was the basis of the null space, and this was the extension. So everything in V can be written like this. What does T do to that? Well, I better use linearity here because I have no idea what T does to any of this, yeah? I mean, T is applied to this huge sum of vectors. How can I use linearity? Chop it up. So that's what T does to V. What are all these? Oh yeah, because those are all the null space vectors, right? U1 is in the null space and U2 is in the null space all the way up to UM. So this is just this. Okay, so what have we just shown? No, not quite a basis. Not quite, almost. Basis has two, like, what does it mean to be a basis? What two properties do you need? Linearly independent and spanning. What did we just show here? Spanning. So we have a spanning set now. What this says is that the range of everything that comes out of T can be written as a linear combination of the TVIs, right? We don't know it's linearly independent yet. So what we know right now is, so TV1 up to TVN spans the range of T. I've got to go one step further to say that they're linearly independent. Any ideas? Well, how do I show vectors are linearly dependent? C1 TV1 plus Cn tvn is equal to 0. And what do I need to force to be true? All the C's are equal to 0, right?
Wait, show the C's be D.
I mean, they're actually not even D's. I call them something different. I was trying to, yeah, sure. I will be consistent with that. Sorry, that was me being mathematically lazy and recycling notation. Okay, so if this was true, what should we be able to say about the DNs? If these are going to be linearly independent? They're all 0, right? Can we force that to be true? Well, let's see. That means that this would be true whenever this was true. How do I know that this is this? Now I'm going to assert that this is the 0 vector. How do I know this is the 0 vector?
It's 0, 0. Since it's linear, that's property.
Not quite, because other things in the null space could also be sent to 0, right? How do I know that this vector is not some other vector in the null space? Because we defined it that way, right? These vectors were in the null space and everything over here wasn't. The extension does this completely describe the null space, right? Nothing over here can be in the null space because otherwise there would be linear dependence between these sets. So if this is not in the null space, and yet what's the only possible linear combination of V1 through Vn that can be in the null space of T? It's just the 0 vector, right? So D1 V1 up to Dn Vn must be zero. It must be the zero vector because it can't be in the null space. So it can only be the zero vector. Is that enough to conclude that all the D's were zero? How do I know the D's are zero?
Because for it to be linearly independent, altogether multiples of these have to be equal to zero.
Do I know that the V's are linearly independent? They're a subset of a linearly independent set, right? They're part of a basis. They were part of a basis over here. The V's were part of a basis, so they're linearly independent. So since V1 through Vn are linearly independent, that means that D1 up to Dn must have been zero, but that means this expression only held when D1 through Dn was zero, and that means that these vectors were linearly independent. So TV1 up to TVn is linearly independent. And a linearly independent spanning set is a basis. That means that the dimension of V, which was m plus n, is equal to the dimension of the null space of T, which was m, plus the dimension of the range of T, which is n. Now, I would not put this in the category of an easy argument because there's a lot of pieces here. Like the different lines of this, the steps of this are interacting with previous steps in a pretty complicated way. Spend some time reading this one again, because this trick of moving back and forth and using the fact that we have linear dependence relations like this is a common theme in the sort of exercises that we're doing, right? Yep. Okay. Do you just want to know, or you got a specific question about it?
Oh no, I think
Okay. So yeah, this is actually the core. So this argument actually is mostly mechanical. So almost all these arguments have one subtle step in, right? This step right here is the heart of the entire argument. How do you know that this must be the zero vector? And the answer is, well, what would it mean for this expression to be? What does this mean for this expression to hold? It would mean that this vector was in the null space, right? And what that would mean is, okay, so if T of D1, V1 up to Dn, Vn is equal to zero, then that means D1, V1 up to Dn, Vn is in the null space of T. But to be in the null space of T means you can be expressed as a linear combination of the U's, right? So that means C1U1 plus CNUM is equal to D1, V1 up to Dn, Vn. If this is in the null space, I can write it in this basis. And if you subtract it all over to one side, you get this. What would it mean for this to have non-zero coefficients? It would be linearly dependent. Is that possible? No, because this is a basis for V, right? If it's a basis that's linearly independent, those coefficients cannot be zero because this is a basis, which means it cannot, that means they all must be zero. And that means that this must be the zero vector. Yep.
Why is it that we can't end our linear independent proof at the final line on the right side of the board when we say that D1 is D1 TV1 plus Dn?
Because you don't know that T isn't mapping, say, two vectors onto the same vector. You don't know that TV1 and TV2 aren't landing. I don't know T is one-to-one, right? That's not, there's no one-to-one-ness going here. So at least prior to doing the argument, we don't actually know that TV1 and TV2 aren't somehow landing in the same direction.
Okay, so we only know that D1 and Dn are independent, but not TV1. That's how we
Yeah.
get it.
Yeah, so we're trying to, the question is, okay, so we get here, how are we going to show these are linearly independent? We have to work backwards and use the linear independence of the V's. And so this entire backwards argument comes from trying to get the independence of the V's to play into this. Yep.
how's that line equals to the line below?
How's this line equal to this? Well, I mean, these dudes. So U1 up to UM, those are in the null space of T.
Okay.
So that's what it means to be in the null space, is T turns U into nothing. So that's 0, and 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 that's 0. All these turn into 0 because that's what T does to vectors in its null space. This is in the null space of T. T turns it into 0. 0 plus 0 plus 0. That's what T does to vectors in the null space, is it destroys them. I mean, that we chose these to be a basis for the null space. Yep.
So when you get to the bottom, you have to equate it to 0 in order to then continue. Like you get the 2.
What's that?
If the 2 is equal to 0, you want to.
Yeah, so the idea here is, so we got to this line right here. So what this line shows, this line is the connection between TV and this. This actually shows that it's a spanning set. So that says that the range is in everything that comes out of the range is a linear combination of TV1 through Vn, right? So that means this is a spanning set. But if I want to go one step further and show that it's linearly independent, so I get a basis, that's actually where I start with the definition of linear independence. And that's where the 0 comes from there. So this is sort of like, okay, we stopped this part of the argument. We concluded it's a spanning set. So now let's start over again and look at linear independence instead. Yep.
So like a simple way of putting that point line you said, you can say like that you want to be in and not in the null space. But that's true.
Yeah, basically basically these vectors cannot be in the null space. So the only linear combination that could be in the null space is the 0 vector. And the only way these can combine into the 0 vector is if the coefficients are all 0. So we're sort of like bootstrapping linear independence is what we're doing there. This is one of these arguments that I like. One approach to working through an argument like this, if you don't pick out all the details when I go through on the board, and you shouldn't expect to. If you're sitting here confused or like you lost me somewhere and it just looks like a pile of words on the board, go back and write this argument out step by step. And every time you hit something that you don't understand why that line goes, right? That you should mine that step out, right? Why does Axler say this line is true? Why does he say that line is true? And the only way you can do that is to actually read these things line by line. I know it seems like a lot of work probably to do that, but it's a really effective way of figuring out if you really understand how these arguments work is, okay, he says these two things are equal, but why? He says these two things are equal, but why? Why did I say this, right? If I can look at that and tell you why it's true, but you should also be able to reproduce that if you're sitting down and looking at the argument, whether or not you actually, I mean, some people like find rewriting these proofs is helpful. Some people can just read carefully and annotate. I should encourage you, like, you have to read this stuff, right? When you have electronic copies of the book, pretty much everybody's got some sort of electronic thing, but hopefully you can annotate, because when I read this stuff, the way I did it when I was in school, when I hit this level of class, was I would go through these proofs and I would write little question marks down the line, right next to lines. I had no idea why it happened, right? Like, I do not understand why this stuff works. 3 people came into my office hours today and asked great questions that were, I don't understand how a move like this worked in various proofs. And getting those questions answered is important because those are the same moves you'll be making in your own arguments, right? Remember, this stuff has to be wrestled with. You don't just get it, you don't get it for free, right? It's not like, oh, I totally understand it because, like, you know, my professor wrote it on the board. I'm gonna go home and do 10 homework exercises. Like, you're asking a lot of yourself to do that. It just takes a little bit more work. Okay. All right. Are there any more questions about this? So what is the upshot? Like, so now we wrote a bunch of stuff on the board. What should you take away from this argument? So another thing to do when you read a proof is, what key ideas showed up in the proof that might be worth holding on to? So for me, a key idea in this proof was the idea of creating that basis, right? That if you have a vector space V, that V is basically the span of a basis for its null space and a bit that's going to get turned into the basis for the range. This is, to me, this is the heart of this argument, is that V, if you have some T, this is a basis for the null space of T, and this will become a basis for the range of T. So linear operators basically split vector spaces into two pieces. A piece they turn into nothing, and a piece they actually do something to. Okay? To me, this is the core of the entire argument, is that you can write this down. What I mean here is that TV1 up to TVN span the range of T. That's not true for general functions. It is true for linear functions. Okay, so dimension stuff aside, this idea of cutting a vector space up into pieces like this is really important. Yep.
Sorry, why did you say that we can break it up with the span as a range?
Because what we did in the argument, we built the space. We start with a null space of T, we extended it, and then the extension, once we applied T, turned into a basis for the range, right? But this will happen no matter what function you start with, and no matter what vector spaces you're working on. This technique is always available to you. And what you'll find when you start looking at these homework exercises is they actually expect you to be able to pick out ideas that happen in the proofs, not just using the theorems, but certain ideas that showed up in the proofs. And this is one of those ideas that comes up again. Yep.
How do you know that that's
Well, that's we proved it. That was part of the argument. That was part of our proof. Was we proved that the extension of the basis of V, if I threw away the stuff in the null space and applied T to the rest of it, that we proved that this set was a spanning set for the range of T. And we all,
we proved it was linearly independent.
We proved it was linearly independent, and we proved it was the span. Because what we showed, remember the core thing here was to show that TV was equal to C1 TV1 up to D1 up to DN TVN. This statement right here, that for all V this is true, is to say that the range of T is the linear combinations of the TVIs. Yep.
Are you saying that a linear map splits up the vector space?
Yep. That's a core feature of what linear maps do, is they chop vector spaces up into pieces they send to zero and pieces that they send on just to structure the range. Right? I mean, that's what's going on at the core of this. And later on, when we start doing things like, you know, way in the future, the idea of eigenvalues are going to show up, right? Eigenvalues and eigenvectors are going to show up. And eigenvalues and eigenvectors basically have the same type of idea. It's a way of cutting a vector space up into pieces that get sent to zero, pieces that get sent on to other spaces in terms of a basis like this. So the idea of sort of divvying up a vector spaces into pieces that act differently with respect to a function is one of the core ideas of the study of linear maps. Sorry. Another car one. Three of them. All right. So what I would like you guys to do is, as the sort of best way to get a handle on what happens next here once you have the dimension theorem, is what you can do with it. So you should look at the proofs. In fact, I might ask you guys to prove these for me next time because the proofs are so nice. So look at 3.23 and 3.24. And what I want to say about these, I'm going to tell you what the theorems say. So these are Axer's titles. A map to a smaller space is not injective. Why should that be true? Why should that be true? From a higher dimensional space to a lower dimensional space can't be injective. Why? Like, just forget the dimensions. Just like, why? Why would you think that might be true? Remember, injective means one-to-one. So if I have a map and it goes from R3 into R2, why should you believe that that can't be a one-to-one map? Yeah, you've got 3 dimensions worth of stuff you're trying to crush down into 2 dimensions, right? If you're going to send you got to send all the inputs somewhere. So it's like, okay, I take this 2-dimensional slice and I'll cover all of 2-dimensional space, but then I've got all this other stuff I got to do something with. So you should believe that this is true. And likewise, you should also believe a map to a larger space is not surjective. Why should that be true? So this is like saying a map from R into R2. What does a map from R to R2 look like? Like a parametric curve or something, right? You guys have seen this in calculus. R of t is equal to cosine t sine t. You're going to fill up all 2-dimensional space with a 1-dimensional. I mean, okay, you actually better be careful with that. You actually can fill up 2-dimensional space with a 1-dimensional curve called the space filling curve. But imagine that that doesn't exist, and you just have a linear map, which these are, right? This is saying if you have a small space and you put it into a big space, you can't cover the big space with a small space. The linear map can't do that. Yep. You don't actually need contradiction. In fact, these are immediate from the fundamental theorem of linear maps, right? These are dimension arguments. So if you really want to test yourself on this stuff, I want you to see if you can think of the proofs of these without looking at it in the book. It just as an exercise. Use the fact that the dimension of B is equal to the dimension of the null space of T plus the dimension of the range of T, and see if you can figure out how to use this fact to show those both must hold. They're very difficult arguments if you work with the basis, and they are dead easy if you work with dimension. All right, and if you don't get it, read those proofs too, and we'll talk about them next time. And then, well, let's on Thursday, let's plan about talking about the exam. In fact, I think it's likely that what we're going to do with the exam is that we will be taking it again in an all group setting of class so that people can earn back things that they didn't get. Because I want you guys to master this material. And I saw some things on that test that I want to spend some time talking about. Right? So anticipate that we're going to sort of work through this together as a group, and you'll be able to earn back stuff that you missed. Right? Don't worry, you know, don't panic. Now, those of you that like have yet to take the test, I'd like